So I'd like to talk about discussions around particularly human hearing, also connected to mammalian hearing as well. In terms of questions we see in terms of audible sounds and things that we may not even actually realize that are kind of typical but need to be that might be very helpful and aware, both in terms of understanding biological systems, the biological aspect of it, as well as understanding how we might build synthetic systems, how we build prosthetics, and how we begin to look at these questions. So, what the first thing that's important to realize is that human hearing tends to go from about 10 to 20 hertz, is the way people will talk about it, to about 20 kilohertz. And where you talk about a lot of the speech tends to be between 100 hertz and about 4 kilohertz. Um, what you find is this sort of becomes a much more classic picture of this question. What you see is, you'd say, imagine I have frequency for a stimulation, stimulate a pure tone. And I'm going to do that at a particular intensity level. So either going from, say, 0 dB SPL, and these are sort of pressure levels that we would look at, to anywhere from 0 up to, when people talk about the threshold of pain, is at 140 dB SPL. So you might imagine things like gunshots and so forth sit in this space. Rock concerts often sit at the high end, on the upper levels of the SPL range. In a classic case, yeah, if you have something too loud, you can kind of map out, oh, here's a place of pain, and I don't want to hear any higher than that. I don't want any intensity higher than that. On the other end, you can also say, at what intensity for every frequency do I hear something, right? And I'm going to talk about that at the low end as a threshold. And what most people don't realize is that different frequencies, I have different ranges of which I can hear. So at 100 dB SPL, out of my ears, I can hear a lot of things in a normal functioning body, human hearing system. As I go down in pressure level, that will change. And for humans and or cats, the levels can go down to 0 dB SPL, which is pretty impressive. And you can hear quite clearly at least 120, and so that's 12 orders of magnitude of intensity difference, and that's pretty incredible in terms of dynamic range for any system you build. It's also quite relevant because if I'm sitting there trying to build like electronic systems to capture this, I'm also going to have some struggle here in terms of getting all of the accuracy that I need. I can do a pretty good job, but the question is, when is it good enough? And so I will definitely have cases of different intensity level. Now, interestingly enough, most conversational speech sits around in these spaces, again, about 100 hertz to, about 3 to 4 kilohertz or so. The intensity level, depending on who you are, where you live, is going to be somewhere in the 40, 60, 80, 90 dB SPL. Also depends on if you're talking in a normal room level, or if you're shouting, or wherever it is. And there's a lot of cultural and different influences. Even in the U.S. where I live, that's going to be quite a big difference. The difference between how people would, the intensity level which someone speaks in Georgia to the intensity level people speak, say, in some parts of the northeast part of the U.S. Again, very, very different. Not a right or wrong, just something we have to know when you're kind of building these, when you think through these systems. And so this is kind of the way we look at it, and this is kind of where speech is. So interestingly enough, we're going to have a lot of different questions there. Now, you might say, well, when we actually try to capture these questions, capture acoustics, what do we use? Well, if I'm doing really high quality audio, I'm going to be in the 44.1 kilohertz range or a multiple thereof. There's different numbers and versions of it. 44 kilohertz means I got a pretty good range to do 20 kilohertz bandwidth and below, without having any trouble with Nyquist. Remember, Nyquist means you need to sample at least twice, and you need some room to the analog people to make their filters, and all of that works. Interestingly enough, when you start talking about, wideband audio, that's probably going to be 50 hertz to about 7 kilohertz. So you're already kind of compressed this thing a little bit, but you've got most of it to work with. Very, very nice sort of things. But then as soon as you start talking about telephone standards, like, you typical numbers where you start talking about 8 kilosamples per second. So that's about a 4 kilohertz-ish, actually about 3.4 kilohertz bandwidth to about 300, because you end up sort of building analog filters to sort of wall this. About 300 here, you're like, wait, I'm losing a lot of the low frequency information. In fact, if you look at the primary harmonics of particularly male voices and female voices, they're actually below that number. Now, some of it I'm bringing in because of alias, because sort of it gets through the filter. Some of it's coming through because I'm actually listening to speech in the harmonics, not actually in the primary harmonic. And so I'm getting parts of that. I also only get about 34 dB, which is roughly in the 60 to about 94 dB range, which is typical speech. But I'm certainly only limiting what I can have because the bit rate transmission is always a concern and always has been. And in case you're wondering, cell phones are worse. Normally you're dealing 64-bit per kilobit per second for telephones. Cell phones are significantly less than that, which already should make you wonder a little bit, although maybe it doesn't surprise you that your cell phone quality isn't as good, or maybe it really should surprise you that it's as good as it is. It's actually really remarkable how your brain will kind of fill in all the things that you don't think that you're actually not kind of hearing great. The other thing to understand is that SNR for these systems is always a tough thing because you get a whole bunch of things like interferers and other noise sources in any system. Normally, if you have an acoustic sort of speech waveform and you have 20 dB SNR, that's considered excellent. That's considered a really quiet room. I would imagine if you were actually looking at the SNR of this recording, it's probably going to be pretty close. But typically when you're in a room with multiple speakers and lots of people talking, so therefore you have multiple speakers and things going on, it's not uncommon for SNR to be 0 dB. And this can be kind of terrifying to people who are used to classical sort of engineering analysis, because 0 dB just sounds horrific. And we humans kind of live in those spaces without too much trouble, and 6 dB, 9 dB is pretty nice environments actually for acoustics that we might expect. One other thing that's important here, and particularly from a prosthetic sense, because what can happen is these are the thresholds you get for human for someone who has good hearing. But as people, go through life, that hearing may change. And it doesn't get better. That's a fair thing to say. So these thresholds will increase. And that means that anything that's softer than this level will go away. It also means that the threshold of pain can actually come down a bit, or at least where you're comfortable. And so what happens is that's going to change all the way through for different frequencies. There's no way around this. Different places and different parts in your cochlea are going to have different changes. The hair cells are going to have some of them will continue responding, some will just not, and that will have an effect in terms of the intensity of what you can pick up. And so what you might say is that, let's say at a frequency at say 1 kilohertz, this is the range I would expect to have from here to here, so ideal from there to there. The actual, if I measure it, say going to an audiologist, is they might put in a pure tone and ask the person and go, oh, here's my actual. And you're thinking, well, that's a lot smaller. It might still be okay because I can still get a lot of conversational speech, but not all. And I can get most higher sounds, but not all. And so what I might end up doing is, hey, why don't I take this entire range that I'm getting synthetically from electronics and move it into this tighter range? Seems like a great idea. And imagine I could do this at multiple frequency points. And by the way, typical numbers for doing that is about 8 to 16 bands, 8 to 16 bandpass filters representing the cochlea throughout. Now the cochlea has thousands of bandpass filters. So it's interesting that often with 8 to 16 it's sufficient. It's actually, and that also should be relatively interesting for other sort of speech and other kinds of processing, but that's kind of the numbers that you see. Um, and then how do I do this compression? Well, I'm going from a log scale to a log scale. So you usually do some sort of power law compression. And at the core, that's what most commercial hearing aids do. And then it's a question of there's some dynamics of how do you how do you connect those things up. But that's effectively what the core of it looks like, and certainly has a huge impact for many people. Yes, there's some issues. There's a lot of stuff to fix still, but the fact that it works at all is pretty darn cool. The fact that you can do some related things for cochlear implants, and lots of people are in pretty good shape with that. Again, really cool. So it's a lot of things there, but it's kind of the key thing is that there's a lot of like sort of practical details that are connected of understanding what happens for their acoustics, and a lot of this comes from sort of knowing basic knowledge of cochlear structure and front end structure of the cochlea, and then how to give sort of function back when you have some of these issues.